Terraform is one of the most popular DevOps tools for infrastructure as code. And through the next hour or so, we will take you from being zero to hero through this comprehensive and hands-on course. In this course, we will simplify complex concepts using illustrations and animations, and you will gain hands-on practice through our labs that you can access for free. Yes, our labs open up right in your browser, so you don't have to pay extra for cloud accounts or set up your own infrastructure. In this course, Vijin will walk you through the fundamentals of Terraform and help you not only understand the basics, but also practice and gain hands-on experience. If you're visiting our channel for the first time, don't forget to subscribe as we upload new videos and courses all the time.
Hello and welcome to this course on Terraform for Beginners. My name is Vijin Palazi and I will be your instructor for this course. In this course, we will get started with Terraform. But first, we will take a look at Infrastructure as Code or IAC and the different types of tools available in IAC and their purpose in managing the modern IT infrastructure. We will then see the role of Terraform in today's IT infrastructure. Then, we will learn how to install Terraform. This is followed by the basics of Hashicorp configuration language. Next, we have our very first lab, where you'll get your hands dirty working with the HCL syntax. Next, we will understand the basics of Terraform, such as providers, input and output variables, resource attributes, and dependencies. After this, we will take a look at state in Terraform, what it is, why it is used, and the considerations to follow when working with state. We then dig deeper into the fundamentals, starting with different commands provided by Terraform. This is followed by a lecture where we understand the difference between mutable and immutable infrastructure. Next, we'll take a look at lifecycle rules in Terraform, where we'll learn how to manage the ways in which resources are created. After this, we have lectures on basic topics such as data sources, meta-arguments such as count and for each, and finally understand version constraints in Terraform. So let's get started. Let's now get introduced to our labs. To access the labs, go to this link. This link is also available in the description below. If you're visiting KodeKloud for the first time, then sign up for free. And once in, you will find the lab course under your list of courses. The course has multiple scenarios. I will let you know when to access the other labs as you progress through this course. So head over to KodeKloud to access the labs. Let's start with how application delivery works in a traditional infrastructure model and how it evolved with the emergence of technologies such as cloud computing and infrastructure as code. Let's go back in time and look at how infrastructure was provisioned in the traditional IT model. Let us consider an organization that wants to roll out a new application. The business comes up with the requirements for the application. The business analyst then gathers the needs from the business, analyzes it, and converts it into a set of high-level technical requirements. This is then passed on to a solution architect. The solution architect then designs the architecture to be followed for the deployment of this application. This would typically include the infrastructure considerations such as the type, spec, and count of servers that are needed, such as those for front-end web servers, back-end servers, databases, load balancers, etc. Following the traditional infrastructure model, these would have to be deployed in the organization's on-premise environment, which would mean making use of the assets in the data center. If additional hardware is needed, they would have to be ordered via the procurement team. This team will put in a new hardware request with the vendors. It can then take anywhere between a few days to weeks or even months for the hardware to be purchased and delivered to the data center. Once received at the data center, the field engineers would be in charge of rack and stack of the equipment. The system administrators perform initial configurations, and the network administrators make the systems available on the network. The storage admins assign storage to the servers, and the backup admins configure backups. And finally, once the systems have been set up as per the standards, they can then be handed over to the application teams to deploy their applications. This deployment model which is still quite commonly used today, has quite a few disadvantages. The turnover time can range between weeks to months, and that's just to get the systems in a ready state to begin the application deployment. This includes the time it takes for the system to be initially procured and then handed over between teams. Also, scaling up or scaling down the infrastructure on demand cannot be achieved quickly. The overall cost to deploy and maintain this model is generally quite high. While some aspects of the infrastructure provisioning process can be automated, several steps such as the rack and stack, cabling, and other deployment procedures are manual and slow. With so many teams working on so many different tasks, chances of human error are high, and this results in inconsistent environments. Another major disadvantage of using this model is the underutilization of the compute resources. The infrastructure sizing activity is generally carried out well in advance, and the servers are sized considering the peak utilization. The inability to scale up or down easily means that most of these resources would not be used during off-peak hours. In the past decade or so, organizations have been moving to virtualization and cloud platforms to take advantages of services provided by major cloud providers such as Amazon AWS, Microsoft Azure, Google Cloud Platform, etc. By moving to cloud, the time to spin up the infrastructure and the time to market for applications are significantly reduced. This is because with cloud, you do not have to invest in or manage the actual hardware assets that you normally would in case of a traditional infrastructure model. The data center, the hardware assets, and the services are managed by the cloud provider. A virtual machine can be spun up in a cloud environment in a matter of minutes, and the time to market is reduced from several months, as in the case of a traditional infrastructure, to weeks in a cloud environment. And infrastructure costs are reduced when compared with the additional data center management and human resources cost. Cloud infrastructure comes with support for APIs, and that opens up a whole new world of opportunity for automation. And finally, the built-in auto-scaling and elastic functionality of cloud infrastructure reduces resource wastage. With virtualization and cloud, you could now provision infrastructure with a few clicks. While this approach is certainly faster and more efficient when compared to the traditional deployment methods, using the management console for resource provisioning is not always the ideal solution. It is okay to have this approach when we are dealing with limited number of resources, but in a large organization with elastic and highly scalable cloud environment with immutable infrastructure, this approach is not feasible. Once provisioned, the systems still have to go through different teams with a lot of process overhead that increases the delivery time. And the chances of human error are still at large, resulting in inconsistent environments. So different organizations started solving these challenges within themselves by developing their own scripts and tools. While some use simple shell scripts, others use programming languages such as Python, Ruby, Perl, or PowerShell. Everyone was solving the same problems, trying to automate infrastructure provisioning to deploy environments faster and in a consistent fashion by leveraging the API functionalities of the various cloud environments. These evolved into a set of tools that came to be known as infrastructure as code. In the next lecture, we will see what infrastructure as code is in more detail. In this lecture, we will get introduced to infrastructure as code, which is commonly known as IAC. We will also take a look at commonly used IAC tools. So earlier, we discussed about provisioning by making use of the management console of various cloud providers. The better way to provision cloud infrastructure is to codify the entire provisioning process. This way, we can write and execute code to define, provision, configure, update, and eventually destroy infrastructure resources. This is called as infrastructure as a code, or IAC. With infrastructure as code, you can manage nearly any infrastructure component as code, such as databases, networks, storage, or even application configuration. The code you see here is a shell script. However, it is not easy to manage it. It requires programming or development skills to build and maintain. There's a lot of logic that you will need to code, and it is not easily reusable. And that's where tools like Terraform and Ansible help with code that is easy to learn, is human readable, and maintain. A large shell script can now be converted into a simple Terraform configuration file like this. With infrastructure as code, we can define infrastructure resources using simple, human-readable, high-level language. Here is another example where we'll be making use of Ansible to provision 3 AWS EC2 instances, making use of a specific AMI. Although Ansible and Terraform are IAC tools, they have some key differences in what they are trying to achieve. And as a result, they have some very different use cases. We will see these differences next. There are several different tools part of the infrastructure as code family: Ansible, Terraform, Puppet, CloudFormation, Packer, SaltStack, Vagrant, Docker, etc. Although you can possibly make use of any of these tools to design similar solutions, they have all been created to address a very specific goal. With that in mind, IAC can be broadly classified into 3 types. Configuration management. Ansible, Puppet, SaltStack fall into this category. Tools used for server templating. Docker, Packer, and Vagrant fall into this category. And finally, we have infrastructure provisioning tools such as Terraform and CloudFormation. Let's look at these in a bit more detail. The first type of IAC tool that we are going to take a look at is configuration management tools. These include tools like Ansible, Chef, Puppet, and SaltStack. And these are commonly used to install and manage software on existing infrastructure resources such as servers, databases, networking devices, etc. Unlike the ad hoc shell scripts that we saw earlier, configuration management tools maintain a consistent and a standard structure of code, and this makes it easier to manage and update it as needed. They are also designed to run on multiple remote resources at once. An Ansible playbook or a role can be checked into a version control repository. This allows us to reuse and distribute it as needed. However, perhaps the most important feature of a configuration management tool is that they are idempotent. This means that you can run the code multiple times, and every time you run it, it will only make changes that are necessary to bring the environment into a defined state. It would leave anything already in place as it is, without us having to write any additional code. Next, let's look at server templating tools. These are tools like Docker, Vagrant, and Packer from Hashicorp that can be used to create a custom image of a virtual machine or a container. These images already contain all the required software and dependencies installed on them. And for the most part, this eliminates the need of installing software after a VM or a container is deployed. The most common examples for server templated images are VM images, such as those that are offered on osboxes.org, custom AMIs in Amazon AWS, and Docker images on Docker Hub and other container registries. Server templating tools also promote immutable infrastructure, unlike configuration management tools. This means that once the VM or a container is deployed, it is designed to remain unchanged. If there are changes to be made to the image, instead of updating the running instance, like in the case of configuration management tools such as Ansible, we update the image and then redeploy a new instance using the updated image. We have a section on immutable infrastructure later in this course where we look at it in much more detail. The last type of IAC tool, which is specifically of interest for this course, is provisioning tools. These tools are used to provision infrastructure components using a simple declarative code. These infrastructure components can range from servers such as virtual machines, databases, VPCs, subnets, security groups, storage, and just about any service based on the provider we choose. While CloudFormation is specifically used to deploy services in AWS, Terraform is vendor agnostic and supports provider plugins for almost all major cloud providers. In the upcoming lecture, we will see how Terraform helps in provisioning infrastructure. Let's now talk about Terraform and go over some of its features at a high level. As we discussed, Terraform is a popular IAC tool which is specifically useful as an infrastructure provisioning tool. Terraform is a free and open source tool which is developed by Hashicorp. It installs as a single binary which can be set up very quickly, allowing us to build, manage, and destroy infrastructure in a matter of minutes. One of the biggest advantages of Terraform is its ability to deploy infrastructure across multiple platforms, including private and public cloud, such as on-premise vSphere cluster or cloud solutions such as AWS, GCP, or Azure, to name a few. These are just a few of the many resources that Terraform can manage. So, how does Terraform manage infrastructure on so many different kinds of platforms? This is achieved through providers. A provider helps Terraform manage third-party platforms through their API. Providers enable Terraform manage cloud platforms like AWS, GCP, or Azure, as we have just seen, as well as network infrastructure like BigIP, Cloudflare, DNS, Palo Alto Networks, and Infoblox, as well as monitoring and data management tools like Datadog, Grafana, Auth0, Wavefront, and Sumo Logic. Databases like InfluxDB, MongoDB, MySQL, PostgreSQL, and version control systems like GitHub, Bitbucket, or GitLab. Terraform supports hundreds of such providers and as a result can work with almost every infrastructure platform. Terraform uses HCL, which stands for Hashicorp Configuration Language, which is a simple declarative language to define the infrastructure resources to be provisioned as blocks of code. All infrastructure resources can be defined within configuration files that has a .tf file extension. The configuration syntax is easy to read and write and pick up for a beginner. This sample code is used to provision a new EC2 instance on the AWS cloud. This code is declarative and can be maintained in a version control system, allowing it to be distributed to other teams. We cover the HCL syntax in more detail later in this course. We also have lots of hands-on labs where you will be practicing working with these files and gain a lot of experience by the end of this course. So we said that the code is declarative, but what does declarative mean? The code we define is the state that we want our infrastructure to be in. That's the desired state. And this on the right is the current state, where there's nothing. Terraform will take care of what is required to go from the current state to the desired state without us having to worry about how to get there. So, how does Terraform do that? Terraform works in three phases: init, plan, and apply. During the init phase, Terraform initializes the project and identifies the providers to be used for the target environment. During the plan phase, Terraform drafts a plan to get to the target state. And then, in the apply phase, Terraform makes the necessary changes required on the target environment to bring it to the desired state. If for some reason the environment was to shift from the desired state, then a subsequent Terraform apply will bring it back to the desired state by only fixing the missing component. Every object that Terraform manages is called a resource. A resource can be a compute instance, a database server in the cloud, or in a physical server on-premise that Terraform manages. Terraform manages the lifecycle of resources from its provisioning to configuration to decommissioning. Terraform records the state of the infrastructure as it is seen in the real world, and based on this, it can determine what actions to take when updating resources for a particular platform. Terraform can ensure that the entire infrastructure is always in the defined state at all times. The state is a blueprint of the infrastructure deployed by Terraform. Terraform can read attributes of existing infrastructure components by configuring data sources. This can later be used for configuring other resources within Terraform. Terraform can also import other resources outside of Terraform that were either created manually or by the means of other IAC tools and bring it under its control so that it can manage those resources going forward. Terraform Cloud and Terraform Enterprise provide additional features that allow simplified collaboration between teams managing infrastructure, improved security, and a centralized UI to manage Terraform deployments. All these features make Terraform an excellent enterprise-grade infrastructure provisioning tool. Well, that was a quick introduction to Terraform at a high level. So let's dive in and explore all of these in much more detail in the upcoming lectures. In this section, we will learn how to install Terraform. Terraform can be downloaded as a single binary or an executable file from the Terraform download section in www.terraform.io. Installing Terraform is as simple as downloading this file and copying it to the system path. Once installed, we can check the version by running the command terraform version. The latest version of Terraform as of this recording is 0.13, and we'll be making use of this version throughout the course. Terraform is supported on Windows, Mac, and several other Linux-based distributions. Please note that all the examples and labs used in this course will make use of Terraform running on a Linux machine and specifically the version 0.13. And that's it. We can now start deploying resources using Terraform. As stated earlier, Terraform uses configuration files which are written in HCL to deploy infrastructure resources. These files have a .tf extension and can be created using any text editor such as Notepad or Notepad++ for Windows, or command line text editors such as Vim or Emac in Linux, or it could be any IDE of your choice. So, what is a resource? A resource is an object that Terraform manages. It could be a file on a local host, or it could be a virtual machine on the cloud such as an EC2 instance, or it could be services like S3 buckets, ECS, DynamoDB tables, IAM users or IAM groups, roles, policies, etc. Or it could be resources on major cloud providers such as the Compute and App Engine from GCP, databases on Azure, Azure Active Directory, etc. There are literally hundreds of resources that can be provisioned across most of the cloud and on-premise infrastructure using Terraform. We will look into some of these examples later in this course, but for the first few sections, we will stick to two very easy to understand resources: the local file type of resource and a special kind of resource called a random pet. It is important to use a simple resource type to really understand the basics of Terraform, such as the lifecycle of resources, the HCL format, etc. Once we gain a good understanding of the basics, we can easily apply that knowledge to other real-life use cases, and we will see that in later sections of this course. In this lecture, we will understand the basics of HCL, which is Hashicorp configuration language, and then create a resource using Terraform. Let us first understand the HCL syntax. The HCL file consists of blocks and arguments. A block is defined within curly braces, and it contains a set of arguments in key value pair format representing the configuration data. But what is a block, and what arguments does it contain? In its simplest form, a block in Terraform contains information about the infrastructure platform and a set of resources within that platform that we want to create. For example, let us consider a simple task. We want to create a file in the local system where Terraform is installed. To do this, first let us create a directory called terraform-local-file under the /root directory. This is the directory under which we will create the HCL configuration file. Once we change into this new directory, we can create a configuration file called local.tf. And within this file, we can define a resource block like this. And inside the resource block, we specify the file name to be created as well as its contents using the block arguments. Let us break down the local.tf file to understand what each line means. The first element in this file is a block. Now this can be identified by the curly braces inside. The type of block we see here is called the resource block, and this can be identified by the keyword called resource in the beginning of the block. Following the keyword called resource, we have the declaration of the resource type that we want to create. This is a fixed value and depends on the provider where we want to create the resource. In this case, we have the resource type called local file. A resource type provides two bits of information. First is the provider, which is represented by the word before the underscore in the resource type. Here, we are making use of the local provider. The word following the underscore, which is file in this case, represents the type of resource. The next and final declaration in this resource block is the resource name. This is the logical name used to identify the resource, and it can be named anything. But in this case, we have called it pet, as the file we are creating contains information about pets. And within this block and inside the curly braces, we define the arguments for resource which are written in key value pair format. These arguments are specific to the type of resource we are creating, which in this case is the local file. The first argument is the file name. To this, we assign the absolute path to the file we want to create. In this example, it is set to /root/pets.txt. Now we can also add some content to this file by making use of the content argument. To this, let us add the value "we love pets." The words file name and content are specific to the local file resource we want to create, and they cannot be changed. In other words, the resource type of local file expects that we provide the argument of file name and content. Each resource type has specific arguments that they expect. We will see more of that as we progress through the course. And that's it. We now have a complete HCL configuration file that we can use to create a file by the name of pets.txt. This file will be created in the /root directory, and it will contain a single line of data. The resource block that we see here is just one example of the configuration blocks used in HCL, but it is also a mandatory block needed to deploy a resource using Terraform. Here is an example of a resource file created for provisioning an AWS EC2 instance. The resource type is AWS_instance. We name the resource web server, and the arguments that we have used here is the AMI ID and the instance type. Here is another example of a resource file used to create an AWS S3 bucket. The resource type in this case is AWS_S3_bucket. The resource name that we have chosen is data, and the arguments that we have provided is the bucket name and the ACL. A simple Terraform workflow consists of 4 steps. First, write the configuration file. Next, run the Terraform init command. And after that, review the execution plan using the Terraform plan command. Finally, once we are ready, apply the changes using the Terraform apply command. With the configuration file ready, we can now create the file resource using the Terraform commands as follows. First, run the Terraform init command. This command will check the configuration file and initialize the working directory containing the .tf file. One of the first things that this command does is to understand that we are making use of the local provider based on the resource type declared in the resource block. It will then download the plugin to be able to work on the resources declared in the .tf file. From the output of this command, we can see that Terraform init has installed a plugin called local. Next, we are ready to create the resource. But before we do that, if you want to see the execution plan that will be carried out by Terraform, we can use the command Terraform plan. This command will show the actions that will be carried out by Terraform to create the resource. Terraform knows that it has to create resources, and this is displayed in the output similar to a diff command in Git. The output has a plus symbol next to the local file type resource called pet. This includes all the arguments that we specified in the .tf file for creating the resource. But you'll also notice that some default or optional arguments which we did not specifically declare in the configuration file is also displayed on the screen. The plus symbol implies that the resource will be created. Now remember, this step will not create the infrastructure resource yet. This information is provided for the user to review and ensure that all the actions to be performed in this execution plan is desired. After the review, we can create the resource. And to do this, we will make use of the Terraform apply command. This command will display the execution plan once again, and it will then ask the user to confirm by typing yes to proceed. Once we confirm, it will proceed with the creation of the resource, which in this case is a file. We can validate that the file was indeed created by running the cat command to view the file.
We can also run the Terraform show command within the configuration directory to see the details of the resource that we just created. This command inspects the state file and displays the resource details. We will learn more about this command and the state in a later lecture.
So we have now created our first resource using Terraform. Before we end this section, let us go back and look at the configuration blocks in local.tf file. In this example, we used the resource type of local file and learned that the keyword before the underscore here is the provider name called local. But how do we know that? How do we know what resource types other than local file are available under the provider called local? And finally, how do we know what arguments are expected by the local file resource? Earlier, we mentioned that Terraform supports over 100 providers, including the local provider we have used in this example. Other common examples are AWS to deploy resources in Amazon AWS Cloud, Azure, GCP, Ali Cloud, etc. Each of these providers have a unique list of resources that can be created on that specific platform. And each resource can have a number of required or optional arguments that are needed to create that resource. And we can create as many resources of each type as needed. It is impossible to remember all of these options, and of course, we don't have to do that. Terraform documentation is extremely comprehensive, and it is the single source of truth that we need to follow. If we look up the local provider within the documentation, we can see that it only has one type of resource called the local file. Under the arguments section, we can see that there are several arguments that the resource block accepts, out of which only one is mandatory, the file name. The rest of the arguments are optional. That's it for this lecture. Now let's head over to the hands-on labs and practice working with HCL and create our first resource using Terraform. This is an introductory video to give you a quick tour of the hands-on labs available in this course. Each lab is specially designed to help you practice and gain knowledge on the topics that we learned in the associated lectures and demos. Click on this button to open the hands-on lab and wait for the lab environment to load. It can take up to a minute. The lab interface has two sections. The terminal for the IAC server is on the left-hand side, and this is where you will be running the commands and carrying out tasks based on the questions that's asked. The questions can be found in the quiz portal, which is on the right-hand side of the split screen. There are two types of questions that you can expect. The first type is a multiple choice question, where you'll have to look up the answer for a specific question. Some of these may be straightforward, but for some of them, you'll have to inspect the Terraform configuration from the terminal. For example, to answer this question, we have to navigate to a specific path and inspect the extension of the file that is created inside. One way to do this is from the terminal on the left-hand side. We can see that there is a file called main.tf created in this directory. So let's go back to the quiz portal and select .tf as our answer for this question. The second type of question is a configuration test. For these questions, you'll have to carry out specific tasks such as writing Terraform configuration files and running the Terraform workflow to create, update, or destroy infrastructure. For example, here we have to run the Terraform init command within the same configuration directory. This can again be done using the terminal on the left-hand side. If you are unsure how to attempt a question, click on the hint button, which will provide you helpful hints and point you to the right direction. Once you get to the AWS sections of this course, you will get to work with AWS services. The labs are integrated with an AWS test framework, which will allow you to build, update, and destroy resources on AWS. For example, this question requires us to create an IAM user called Mary and then run Terraform init in the configuration directory. The hands-on labs of this course is slightly different from our other courses. To optimize the learning experience with Terraform, we have integrated the Visual Studio Code IDE into the lab. This will allow you to make use of the built-in Terraform extensions that will help you write Terraform configurations file quickly and efficiently. To access Visual Studio Code, click on the VS Code tab on the top of the terminal, which will open it up in a new tab. From here, we can open the configuration directories on the IAC server and navigate to the path specified in the question. We can also make use of the Terraform extensions which are pre-installed. To answer this question, let's create a file called iamuser.tf in the IAM directory. To easily create a resource block, let's use the command completion feature. This will load the template for the resource block. Next, for the resource type, just type in AWS and press Ctrl and spacebar together. This will list all the resource types available in AWS. We can now type IAM and select the appropriate resource type, which in this case is AWS IAM user. We can also look up arguments for this resource block the same way. Inside the block, press Ctrl and spacebar to see a list of all available arguments and choose the ones that you need. Once ready, run Terraform commands from the terminal. We can also do this from within VS Code. We can right-click inside the directory and click on Open in Integrated Terminal. This will open up the Bash terminal on the bottom of the screen. Well, that's it for this video. We wish you an excellent learning experience ahead. In this lecture, we will learn how to update and destroy infrastructure using Terraform. In the previous lecture, we saw how to create a local file. Now, let us see how we can update and destroy this resource using Terraform. First, let us try to update this resource. Let us add in a file permission argument to update the permission of the file to 0700 instead of the default value of 0777. This will remove any permission for everyone else except the owner of the file. Now, if we run Terraform plan, we will see an output like this. From the output, we can see that the resource will be replaced. The ± symbol in the beginning of the resource name in the plan implies that it will be deleted and then recreated. The line with the comment that reads forces replacement is responsible for the deletion and recreation. And in this example, this is caused by the file permission argument that we added to the configuration file. Even though the change we made was trivial, Terraform will delete the old file and then create a new file with the updated permissions. This type of infrastructure is called an immutable infrastructure. We saw this briefly when we discussed the different types of IAC tools. If you want to go ahead with the change, use the Terraform apply command and then type yes when prompted. Upon confirmation, the existing file is deleted and recreated with the new permissions. To delete the infrastructure completely, run the Terraform destroy command. This command shows the execution plan as well, and you can see the resource and all of its arguments have a minus symbol next to them. This indicates that the resource will be destroyed. To go ahead with the destroy, confirm yes in the prompt. This will delete all the resources in the current configuration directory. In this example, it deletes the file /root/pets.txt. That's it for this lecture. Let's head over to the hands-on labs and practice updating and deleting infrastructure resources using Terraform. In this lecture, let's take a look at providers in more detail. We saw in the previous lecture that after we write a Terraform configuration file, the first thing to do is to initialize the directory with the Terraform init command. When we run Terraform init within a directory containing the configuration files, Terraform downloads and installs plugins for the providers used within the configuration. These can be plugins for cloud providers such as AWS, GCP, Azure, or something as simple as the local provider that we use to create a local file type resource. Terraform uses a plugin-based architecture to work with hundreds of such infrastructure platforms. Terraform providers are distributed by Hashicorp and are publicly available in the Terraform registry at the URL registry.terraform.io. There are 3 tiers of providers. The first one is the official provider. These are owned and maintained by Hashicorp and include the major cloud providers such as AWS, GCP, and Azure. The local provider that we have used so far is also an official provider. The second type of provider is a verified provider. A verified provider is owned and maintained by a third-party technology company that has gone through a partner provider process with Hashicorp. Some of the examples are the big IP provider from FI Networks, Heroku, DigitalOcean, etc. And finally, we have the community providers that are published and maintained by individual contributors of the Hashicorp community. The Terraform init command, when run, shows the version of the plugin that is being installed. In this case, we can see that the plugin name Hashicorp/local with the version 2.0.0 has been installed in the directory. The Terraform init is a safe command, and it can be run as many times as needed without impacting the actual infrastructure that is deployed. The plugins are downloaded into a hidden directory called .terraform/plugins in the working directory containing the configuration files. In our example, the working directory is /root/terraform-local-file. The plugin name that you see here, Hashicorp/local, is also known as the source address. This is an identifier that is used by Terraform to locate and download the plugin from the registry. Let's take a closer look at the format of the name. The first part of the name, which in this case is Hashicorp, is the organizational namespace. This is followed by the type, which is the name of the provider, such as local. Other examples of providers are AWS, Azure RM, Google, Random, etc. The plugin name can also optionally have a hostname in front. The hostname is the name of the registry where the plugin is located. If omitted, it defaults to registry.terraform.io, which is Hashicorp's public registry. Given the fact that the local provider is stored in the public Terraform registry within the Hashicorp namespace, the source address for it can be represented as registry.terraform.io/hashicorp/local, or simply by Hashicorp/local by omitting the hostname. By default, Terraform installs the latest version of the provider. Provider plugins, especially the official ones, are constantly updated with newer versions. This is done to bring in new functionality or to add in bug fixes. And these can introduce breaking changes to your code. We can lock down our configuration files to make use of a specific provider version as well. We will see how to do that later in this course. Now, let's take a look at the configuration directory and the file naming conventions used in Terraform. So far, we have been working with a single configuration file called local.tf, and this is within the directory called terraform-local-file, which is our configuration directory. This directory is not limited to one configuration file. We can create another configuration file like this. The cat.tf is another configuration file that makes use of the same local_file resource. When applied, it will create a new file called cat.txt. Terraform will consider any file with the .tf extension within the configuration directory. Another common practice is to have one single configuration file that contains all the resource blocks required to provision the infrastructure. A single configuration file can have as many number of configuration blocks that you need. A common naming convention used for such a configuration file is to call it the main.tf. There are other configuration files that can be created within the directory, such as the variables.tf, outputs.tf, and providers.tf. We will talk more about these files in the later sections of this course. Now, let's head over to the hands-on labs and explore working with providers. In this lecture, we will see how to use multiple providers and resources in Terraform. Until now, we have been making use of a single provider called local to deploy a local file in the system. Terraform also supports the use of multiple providers within the same configuration. To illustrate this, let's make use of another provider called random. This provider allows us to create random resources such as a random ID, a random integer, a random password, etc. Let us see how to use this provider and create a resource called random pet. This resource type will generate a random pet name when applied. By making use of the documentation, we can add a resource block to the existing main.tf file like this. Here, we are making use of the resource type called random pet. In an earlier lecture, we saw that the resource type can be broken down to two parts. The keyword before the underscore is the provider, which in this case is random. The keyword following it is the resource type, which is the pet. Let's call this resource myPet. Within this resource block, we will use three arguments. One is the prefix that is to be added to the pet name. The second argument is the separator between the prefix and the pet name that is generated. The final argument is the length, which is the length of the pet name to be generated in words. Our main.tf file now has resource definition for two different providers. One resource of the local file type that we have already created earlier, and another resource of type random pet. Before we generate an execution plan and create these resources, we have to run the Terraform init command again. Now this is a mandatory step as the plugin for the random provider should be initialized in the configuration directory before we can make use of it. In the command output of the Terraform init, we can see that the local provider was previously installed and it will be reused. The plugin for the random provider, on the other hand, will be installed as it was not used before. We can now run the Terraform plan to review the execution plan. As expected, the local file resource called pet will not be updated, as it is unchanged from the previous apply. A new resource by the name of myPet will be created based on the new resource block that we just added. Now let's apply the configuration using Terraform apply. As expected, the local file resource is left as it is. But now a new resource has been created which is called myPet. Random provider is a logical provider and it displays the results of the pet name on the screen like this. Here, an attribute called ID, which contains the name of the pet, is returned by the apply command. Before we move on, please note that in our illustration, the dog icon stands for a pet, and we'll be making use of it throughout this course. The random pet can generate any pet name, and it does not have to be specifically a dog. And now, let's head over to the hands-on labs and explore working with multiple providers in Terraform. In this lecture, we will see how to make use of variables in Terraform. We have used several arguments in our Terraform block so far. For the local file, we have a file name and content. And for the random pet resource, we have used the prefix, separator, and length as the arguments. Since these values are directly defined within the main configuration files, they are considered to be hard-coded values. Hard-coding values is not a good idea. For one, this limits the reusability of the code, which defeats the purpose of using IAC. We want to make sure that the same code can be used again and again to deploy resources based on a set of input variables that can be provided during the execution. And that is where input variables come into the picture. Just as in any general purpose programming language, such as Bash scripting or PowerShell, we can make use of input variables in Terraform. To assign variables, let us create a new configuration file called variables.tf and define the values like this. The variables.tf file, just like the main.tf file, consists of blocks and arguments. To create a variable, use the keyword called variable. This is followed by the variable name. This can be named anything, but as a standard, use an appropriate name, such as the argument name for which we are using the variable. Within this block, we can provide a default value for the variable. This is an optional parameter, but it is a quick and simple way to assign values to the variables. We will see the other methods to do so in a later lecture. Great! Now we have our variable configuration file. But how do we use it within the main.tf file? To do this, we can replace the argument values with the variable names prefixed with a var, like this. When using variables, you do not have to enclose the values inside double quotes, as you would when providing actual values. And using the same execution flow that we have seen many times by now, we can create the resources using Terraform plan followed by the Terraform apply. The resources have now been created as expected. Now, if you want to make an update to the resources by making changes to the existing arguments, we can do that by just updating the variables.tf file. The main.tf need not be modified. For example, let us update the local file resource to create the file at the same location but with an updated content that reads, "My favorite pet is Mrs. Whiskers." And for the random pet resource, let's change the length of the pet name to 2. We can do that like this. As expected, when we run Terraform apply, it will recreate the resources. The content of the file has been changed and the pet name now has 2 words following the prefix. Before we conclude this lecture, here's an example of what our configuration files would look like when creating an EC2 instance in AWS with Terraform while making use of input variables. Don't worry if the resource block and the arguments are unfamiliar. We have a separate lecture where we'll be making use of AWS resources later in the course. In this lecture, we will take a close look at the variables block in Terraform. First, let us look at the different arguments that a variable block uses. The variable block in Terraform accepts 3 parameters. The first one, which we have already used, is the default parameter. This is where we specify the default value for a variable. The others are type and description. Description is optional, but it is a good practice to use this argument to describe what the variable is used for. The type argument is optional as well, but when used, it enforces the type of variable being used. The basic variable types that can be used are string, number, and boolean. String variables, as we have seen in our example so far, accept a single value which can be alphanumeric, that is, consisting of alphabets and numbers. The number variable type accepts a single value of a number, which can be positive or negative. And the Boolean variable type accepts a value of true or false. The type parameter, as mentioned previously, is optional. If it is not specified in the variable block, it is set to the type any by default. Besides these three simple variable types, Terraform also supports additional types such as list, map, set, object, and tuple. Let us now see how to use all of these in Terraform. Let us start with list. A list is a numbered collection of values, and it can be defined like this. In this example, we have a variable called prefix that uses a list of values Mr., Mrs., and Sir. But why do we call it a numbered collection? Well, that is because each value, which is also known as an element, can be referenced by their number or index within that list. The index of a list always begins at 0. In this case, the first element of the list at index 0 is the word Mr. The element at index 1 is Mrs. And the final element at index 2 is Sir. These variables can be accessed within a configuration file like this, with the index specified within square brackets. Hence, the expression var.prefix with index 0 uses the value Mr. var.prefix with the index 1 uses the value Mrs. And with index 2, it uses the value of Sir. Next, let us look at the type called map. A map is data represented in the format of key-value pairs. In the variables.tf file, let us create a new variable called fileContent with the type set to map. In the default values, we can specify as many key-value pairs enclosed within curly braces. Here, the statement 1 and statement 2 are keys, and the string data following them are values. Now, to access a specific value from the map within the Terraform configuration file, we can make use of key matching. In this case, we want the content of the local file resource to be the value of the key called statement 2. And for that, we use an expression var.fileContent, which is the name of the map type variable, followed by the matching key within square brackets. We can also combine type constraints. For example, if you want a list of string type elements, we can declare it like this. To use a list of numbers, change it like this. If the variable values used do not match the type of constraint, the Terraform commands will fail. In this example, we have used the type list where the element should be of type number, but the default values are all of type string. Now, when we run Terraform commands such as a plan or an apply, you will see an error like this that states that the default value is not compatible with the variable type constraint, and that a number is required and not a string. And the same is applicable with maps as well. We can use type constraints to make sure that the values of a map are of a specific type. In the first variable block, we are using a map of type string, and in the second one, we are making use of a map that uses numbers. Let us now look at sets. Set is similar to a list. The difference between a set and a list is that a set cannot have duplicate elements. In these examples, we have a variable type of set of strings or a set of numbers. The examples on the left are good, but the ones on the right aren't. They have duplicate values in them that will throw an error. The default values are declared just like you would do for a list, but remember that there shouldn't be any duplicate values here. The next type of variable that we are going to look at are objects. With objects, we can create complex data structures by combining all the variable types that we have seen so far. For example, let us consider a new variable called Bella, which is the name of a cat. This variable is used to define the different features of this cat, such as its name, which is a string, the color, which is a string as well, age, which is a number, the food that it eats, which is a list of strings, and a Boolean value indicating if it's a favorite pet or not. Let us now assign some values to this variable. Let us use name is equal to Bella, color is equal to brown, age is equal to 7, food is fish, chicken and turkey, and favorite pet which is set to true. And we can use the same default values within our variable block like this. The last variable type that we are going to look at is tuples. Tuple is similar to a list and consists of a sequence of elements. The difference between a tuple and a list is that list uses elements of the same variable type, such as string or number. But in case of tuple, we can make use of elements of different variable types. The type of variables to be used in a tuple is defined within the square brackets. In this example, we have three types of elements defined. The first is a string, second is a number, and finally a boolean. The variables to be passed to this should exactly be 3 in number and of that specific type for it to work. Here, we have passed the value of cat to the string element, the number 7 to the number element, and true to the boolean. Adding additional elements or incorrect type will result in an error as seen here. If we add an additional value of dog to the variable, it will fail as the tuple only expects 3 elements of type string, number, and boolean. That's it for this lecture. Let's head over to the hands-on labs and explore working with variable types in Terraform. In this lecture, we will take a look at the different ways in which we can make use of input variables in Terraform. So far, we have created input variables in Terraform and assigned default values to it based on a variable type. This is just one of the ways to pass in values to the variable. Earlier, we learned that the default parameter in a variable block is optional. This means that we can very well have our variable block look like this. But what would happen if we run Terraform commands now? When we run Terraform apply, we will be prompted to enter values for each variable used in an interactive mode. If you do not want to supply values in an interactive mode, we can also make use of command line flags like this. With the Terraform command, we can make use of the -var option with the variable name equals to the value format. We can pass in as many variables as we want with this method by making use of the -var flag multiple times. We can also make use of environment variables with the tf_var_ followed by the name of a declared variable like this. In this example, the tf_var_ file name sets the value of the variable called filename to the value /root/pets.txt. And similarly, the variable called length now has the value of 2. And finally, when we are dealing with a lot of variables, we can load values by making use of variable definition files like this. These variable definition files can be named anything, but should always end in either .tfvars or .tfvars.json. Here, we have declared variables and their values in a file called terraform.tfvars. If you look at the syntax used to create this file, you'll observe that this is using the same syntax of an HCL file, but it only consists of variable assignments. The variable definition file, if called terraform.tfvars or terraform.tfvars.json, or by any other name ending with .auto.tfvars or .auto.tfvars.json, will be automatically loaded by Terraform. If we use any other file name, such as variable.tfvars, for example, you will have to pass it along with a command line flag called -var-file like this. Finally, it is important to note that we can use any of the options that we have seen in this lecture to assign values to the variables. But if we use multiple ways to assign values for the same variable, Terraform follows a variable definition precedence to understand which value it should accept. To illustrate this, let us make use of a simple example. In this case, we have a main configuration file with a single resource, a local file which will create file at a path declared in a variable called filename. In the variables.tf file, we have not specified a default value for this variable. And we have assigned different values to this variable in multiple ways. We have exported the environment variable called tf_var_filename with the value of /root/cats.txt. The terraform.tfvar file has a value of /root/pets.txt for the same variable. We have also made use of a variable definition file with the name variable.auto.tfvars with the value of /root/mypet.txt. And finally, we are also making use of the -var option while running the Terraform apply command with the value of /root/bestpet.txt. So in this case, which one of these values would be accepted? Terraform follows a variable definition precedence order to determine this. First, it loads the environment variables. Next, the value in the terraform.tfvars file. This is followed by any file that ends with the .auto.tfvars or .auto.tfvars.json in an alphabetical order. And finally, Terraform considers the command line flag of -var or -var-file, which takes the highest priority and will override any of the previous values. In this case, the variable file name will be assigned the value of /root/bestpet.txt. That's it for this lecture. Let's head over to the hands-on lab and practice working with the concepts that we learned in this lecture. In this lecture, we will learn how to link two resources together by making use of resource attributes. In the last few lectures, we saw how to use variables to improve the reusability of our code. Right now, we have two resources in our configuration file. Each of this resource has a set of arguments that are used to create that resource. For the file resource, we have used the file name and content as the arguments. And for the pet resource, we have used the prefix, separator, and length. When this configuration is applied, Terraform creates a file and a random pet resource. The name of the random pet is displayed on the screen as an ID, which is Mr. Bull in this case. As it stands, there is no dependency between these two resources. But this rarely ever happens in a real-world infrastructure provisioning process. There are bound to be multiple resources that are dependent on each other. So, what if we want to make use of the output of one resource and use it as an input for another one? What if we want the content of the file to use the name generated by the random pet resource? Currently, the content of the file is set to "My favorite pet is Mr. Cat." But what if we want it to be set to the name that is generated by the random pet resource? To understand this, let us jump back to the documentation for the random pet resource in registry.terraform.io. You would have noticed that there are plenty of examples which are provided in the documentation, including examples for the arguments, but there is also a section called Attribute Reference, which provides the list of attributes returned back from the resource after you run a Terraform apply. In this case, the random pet resource returns just one attribute called ID, which is of type string. The ID is the pet name generated after we run Terraform apply, as we have seen before. Our goal is to make use of the attribute called ID and to make use of it as the content of the local file resource. For this, we can make use of an expression like this. This expression is used to reference the attribute from the resource called mypet. The syntax for using this reference expression is resource type followed by the resource name and the attribute to be used, all of which are separated by a period or a dot. The resource type in this example is random pet. This is followed by mypet, which is the resource name, and the attribute used is ID. You would have also noticed that we are making use of the $ symbol followed by the expression which is enclosed within curly braces. This is known as an interpolation sequence. Since the content argument already uses a string type data, this sequence is used to evaluate the expression given within the curly braces, convert the result to a string, and then insert it to the final string, like this. Now, let us apply the changes made and allow Terraform to recreate the local file. In the output, you can see that the content is being replaced to our desired value and it contains the name of the pet that was generated by the random pet resource. That's it for this lecture. Now, let's head over to the hands-on labs and explore working with reference expressions and resource attributes in Terraform. In this lecture, we will take a look at the different types of resource dependencies in Terraform. In the previous lecture, we saw how to link one resource to another using reference attributes. By making use of reference expression and interpolation, we were able to make use of the output of the random pet resource as an input for the local file resource. Now, when Terraform creates these resources, it knows about the dependency, since the local file resource depends on the output of the random pet resource. As a result, it uses the following order to provision them. First, Terraform creates the random pet resource, and then it creates the local file resource. When resources are deleted, Terraform deletes it in the reverse order, the local file first and then the random pet. This type of dependency is called the implicit dependency. Here, we are not explicitly specifying which resource is dependent on which other resource. Terraform figures it out by itself. However, there is another way to specify dependency within the configuration file. For example, let us make use of the older configuration file without making use of the reference expression for the file content. If we still want to make sure that the local file resource is created after the random pet, we can do this by using the depends on argument like this. Here, we have added a depends on argument inside the resource block for the local file. And we have provided a list of dependencies that include the random pet resource called the myPet. This will ensure that the local file is only created after the random pet resource is created. This type of dependency is called an explicit dependency. Explicitly specifying a dependency is only necessary when a resource relies on some other resource indirectly, and it does not make use of a reference expression as seen in this case. In the later sections of this course, we will see how and when to use this in a real-world use case. Now, let's head over to the hands-on labs and explore working with resource dependencies in Terraform. Let us now look at output variables in Terraform. So far, we have used input variables and reference expressions in our Terraform configuration files. Along with input variables, Terraform also supports output variables. These variables can be used to store the value of an expression in Terraform. For example, let us go back to the configuration file that we used in the previous lecture. We already know that the random pet resource will generate a random pet name using the attribute called ID when we apply the configuration. To save this ID in an output variable called petName, we can create an output block like this. The syntax used to create this output block is the keyword called output followed by the name that we want to call this variable. Inside this block, the mandatory argument for value is the reference expression. We can also add a description, which is an optional argument to describe what this output variable will be used for. Once this block has been created, when we run Terraform apply, we can see that the output variable is printed on the screen. Once the resource has been created, we can also make use of the Terraform output command to print the value of the output variables. The command Terraform output by itself will print all the output variables defined in all the files in the current configuration directory. We can also use this command specifically to print the value of an existing output variable like this. Now, you may wonder where we can make use of these output variables. We already saw that dependent resources can make use of reference expressions to get the output from one resource block as an input to another block. As such, output variables are not really required here. The best use of Terraform output variables is when you want to quickly display details about a provisioned resource on the screen, or to feed the output variables to other IAC tools such as an ad hoc script or Ansible playbook for configuration management and testing. Now, let's head over to the hands-on labs and practice working with output variables. In this lecture, we will see the purpose of using state in Terraform. We already saw how Terraform uses state file to map the resource configuration to the real-world infrastructure. This mapping allows Terraform to create execution plans when a drift is identified between the resource configuration files and the state. Hence, a state file can be considered to be a blueprint of all the resources that Terraform manages out there in the real world. When Terraform creates a resource, it records its identity in the state, be it the local file resource that creates a file in the machine, a logical resource such as the random pet which just throws out the random pet name, or resources in the cloud. Each resource created and managed by Terraform would have a unique ID which is used to identify the resources in the real world. Besides the mapping between resources in the configuration and the real world, the state file also tracks metadata details such as resource dependencies. Earlier, we learned that Terraform supports two types of dependencies, the implicit and the explicit. If we inspect the example configuration file, we can see that we have three resources to provision here. The local file resource called pet depends on the random pet resource. This is evident from the content argument in the local file resource block that uses a reference to the random pet resource. The local file resource called cat is unrelated to the other, and hence it can be created in parallel with the random pet resource. When we apply this configuration, the random pet resource called myPet and the local file called cat can be created first, at the same time. But the local file resource called pet can only be created after the random pet resource is created. We can see that the local file with the name cat and the random pet resource with the name myPet are the first resources to be created. Once that is done, only then is the local file resource called pet created. Until now, we do not rely on state for the provisioning. But what if we decide to delete the random pet resource and the dependent local file from the configuration? Let us now look at what happens when we remove resources from the file. For example, we remove the local file and the random pet resource from the file. If we were to apply the configuration now, Terraform knows that it has to delete these resources. However, in which order does it delete it? Should it delete the random pet resource first or the local file? The information about the resource dependency is no longer available in the configuration file as we have removed those lines from it. This is where Terraform relies on the state and the fact that it tracks metadata. Within the state file, we can clearly see that the local file resource called pet has a dependency on the random pet resource. Since these two resources have now been removed from the configuration, Terraform now knows that it should delete the local file first, followed by the random resource. One other benefit of using state is performance. When dealing with a handful number of resources, it may be feasible for Terraform to reconcile state with the real-world infrastructure after every single Terraform command, such as plan or apply. But in the real world, Terraform would manage hundreds and thousands of such resources. And when these resources are distributed to multiple providers, and especially those that are on the cloud, it is not feasible for Terraform to reconcile state for every Terraform operation. This is because it would take several seconds to several minutes in some cases for Terraform to fetch details about every single resource from all the providers which are configured. For larger infrastructures, this may prove to be too slow. In such cases, the Terraform state can be used as the record of truth without having to reconcile. This would improve the performance significantly. Terraform stores a cache of attribute values for all resources in the state. And we can specifically make Terraform to refer to the state file alone while running commands and bypass having to refresh state every time. To do this, we can make use of the -refresh is equal to false flag with all the Terraform commands that make use of state. When we run the plan with this flag, you can see that Terraform does not refresh state. Instead, it relies on the cached attributes, and in this example, the content which has changed in the configuration file. And as a result, the execution plan plots a resource replacement. The final benefit of state that we are going to look at is collaboration when working as a team. As we have seen in the previous lectures, the Terraform state file is stored in the same configuration directory in a file called terraform.tfstate. In a normal scenario, this means that the state file resides in the folder or a directory in the end user's laptop. This is alright when starting off with Terraform, learning and implementing small projects individually. However, this is far from ideal when working as a team. Every user in the team should always have the latest state data before running Terraform and make sure that nobody else runs Terraform at the same time. Failure to do so can result in unpredictable errors as a consequence. In such a scenario, it is highly recommended to save the Terraform state file in a remote data store rather than to rely on a local copy. This allows the state to be shared between all members of the team securely. Examples of remote state stores are Amazon Web Services S3 service, Hashicorp's console, and Terraform Cloud. We will learn more about remote state stores in much more detail in a later section. We will also learn about Terraform Cloud in a separate section of its own. Now, let's head over to the hands-on labs and explore working with Terraform State. In the previous lectures, we learned about Terraform State and its benefits. Terraform State is the single source of truth for Terraform to understand what is deployed in the real world. However, there are a few things to keep note of when working with state, and we will learn about them in this lecture. State is a non-optional feature in Terraform. However, there are a few considerations. First one is that the state file contains sensitive information. Within it, it contains every little detail about our infrastructure. Here is an example snippet of a state file for an AWS EC2 instance, which is essentially a virtual machine on the AWS cloud. This state file consists of all the attributes for a virtual machine that is provisioned, such as the allocated CPUs, the memory, operating system or the image used, type and size of disks, etc. It also stores information such as the IP address allocated to the VM and the SSH key pair used, etc. For resources such as databases, the state may also store initial passwords. When using local state, the state is stored in plain text JSON files. And as you can see, this information can be classified as sensitive information. And as a result, we need to make sure that the state file is always stored in a secure storage. So, we have two kinds of files in our configuration directory. The Terraform state file that stores state of the infrastructure and the Terraform configuration files that we use to provision and manage infrastructure. When working as a team, it is considered a best practice to store Terraform configuration files in distributed version control systems such as GitHub, GitLab, or Bitbucket. However, owing to the sensitive nature of the state file, it is not recommended to store them in Git repositories. Instead, store the state in remote backend systems such as AWS S3, Google Cloud Storage, Azure Storage, Terraform Cloud, etc. We will see how to work with remote state backends in a dedicated section of its own, but for now it's important to make a note of these considerations. Terraform state is a JSON data structure that is meant for internal use within Terraform. We should never manually attempt to edit the state files ourselves. However, there would be situations where we may want to make changes to the state file, and in such cases, we should rely on Terraform state commands. We will cover these in a later section of the course. Until now, we have seen quite a few Terraform commands in action, such as the Terraform init, plan, and apply. Let us now take a look at some more commands available in Terraform. The first command we will take a look at is the Terraform validate command. Once we write our configuration file, it's not necessary to run Terraform plan or apply to check if the syntax used is correct. Instead, we can make use of the Terraform validate command like this. And if everything is correct with the file, we should see a successful validation message like this. If there's an error in the configuration file, the validate command will show you the line in the file that is causing the error with the hints to fix it. In this example, we have used an incorrect argument for the local file resource. It should be file permission and not file permissions. The next command that we are going to see is the Terraform fmt or the Terraform format command. This command scans the configuration files in the current working directory and formats the code into a canonical format. This is a useful command to improve the readability of the Terraform configuration file. When we run this command, The files that are changed in the configuration directory is displayed on the screen. The Terraform show command prints out the current state of the infrastructure as seen by Terraform. In this example, we have already created the local file resource, and when we run the show command, it displays the current state of the resource, including all the attributes created by Terraform for that resource, such as the file name, file and directory permissions, content, and ID of the resource. Additionally, we can make use of the -JSON flag to print the contents in an JSON format. To see a list of all providers used in the configuration directory, use the Terraform providers command. You can also make use of the mirror subcommand to copy provider plugins needed for the current configuration to another directory, like this. This command will mirror the provider configuration in a new path /root/terraform/new_local_file. We saw how to use Terraform output variables in one of the previous lectures. If you want to print all output variables in the configuration directory, use the command Terraform output. You can also print the value of a specific variable by appending the name of the variable to the end of the output command, like this. The Terraform refresh command is used to sync Terraform with the real-world infrastructure. For example, if there are any changes made to a resource created by Terraform outside its control, such as a manual update, the Terraform refresh command will pick it up and update the state file. This reconciliation is useful to determine what action to take during the next apply. This command will not modify any infrastructure resource, but it will modify the state file. As we saw earlier, Terraform refresh is also run automatically by commands such as Terraform plan and Terraform apply. And this is done prior to Terraform generating an execution plan. This can, however, be bypassed by using the -refresh = false option with the commands. The Terraform graph command is used to create a visual representation of the dependencies in a Terraform configuration or an execution plan. In this example, the local file in our main.tf file has a dependency on the random pet resource. This command can be run as soon as you have the configuration file ready, even before you have initialized the configuration directory with Terraform init. Upon running the Terraform graph command, you should see an output like this. This text generated is hard to comprehend as it is, but it is a graph generated in a format called dot. To make more sense of this graph, we can pass it through a graph visualization software such as GraphViz. And we can install it in Ubuntu using apt, like this. Once installed, we can pass the output of the Terraform graph to the dot command, which we installed using the GraphViz package, and generate a graphic like this. We can now open this file via a browser, and it should show a dependency graph like this. The root is the configuration directory where the configuration for this graph is located. We can see that there are two resources, the local file called pet and the random pet resource called mypet that makes use of the local and the random provider respectively. And finally, we can see that the local file called pet depends on the random pet resource called mypet, as we have used a reference expression in the local file resource that points to the ID of the random pet. That's it for this lecture. Now let's head over to the hands-on labs and explore working with the Terraform commands that we learned in this lecture. In this section, we will learn about the difference between mutable and immutable infrastructure. In one of the previous lectures, we saw that when Terraform updates a resource, such as updating the permissions of a local file, it first destroys it and then recreates it with the new permission. So why does Terraform do that? To understand this, let us make use of a simple example. Consider an application server running Nginx with the version of 1.17. When a new version of Nginx is released, we upgrade the software running on this web server. First from 1.17 to 1.18. And eventually, when a new version 1.19 is released, we upgrade it the same way from 1.18 to 1.19. This can be done using a number of different ways. One simple approach is to download the desired version of Nginx and then use it to manually upgrade the software on the web server during a maintenance window. Of course, we can also make use of tools such as ad hoc scripts or configuration management tools such as Ansible to achieve this. For high availability, instead of relying on one web server, we can have a pool of these web servers, all running the same software and code. We would have to use the same software upgrade lifecycle for each of these servers using the same approach that we used for the first web server. This type of update is known as in-place update. And this is because the underlying infrastructure remains the same, but the software and the configuration on these servers are changed as part of the update. And this here is an example of a mutable infrastructure. Updating software on a system can be a complex task, and in almost all cases, there are bound to be a set of dependencies that have to be met before an upgrade can be carried out successfully. Let us assume that web server 1 and 2 have every dependency met while we try to upgrade the version from 1.18 to 1.19. And as a result, these two servers are upgraded without any issues. Web server 3, on the other hand, does not. The upgrade fails on web server 3 because it has a few dependencies that are not met, and as a result, it remains at version 1.18. The failure in upgrade could be because of a number of reasons, such as network issues impacting the connectivity to the software repository, file system full, or different version of operating system running on web server 3 as compared to the other two. However, the important thing here to note is that we now have a pool of 3 web servers in which one of these servers is running a different version of software as compared to the rest. Over time, with multiple updates and changes to this pool of servers, it is a possibility that each of these servers vary from one another, may it be in software, a configuration, or operating system, etc. This is known as a configuration drift. For example, after a few update windows, our 3 web servers could look like this. Web server 1 and 2 have Nginx version of 1.19 and web server 3 has a version of 1.18. And all 3 web servers may also be running slightly different versions of operating system on them. This configuration drift can leave the infrastructure in a complex state, making it difficult to plan and carry out subsequent updates. Troubleshooting issues would also be a difficult task, as each server would behave slightly differently from the other because of this configuration drift. Instead of updating the software versions on the web servers, we can spin up new web servers with the updated software version and then delete the old web server. So, when we want to update Nginx 1.17 to 1.18, a new server is provisioned with 1.18 version of Nginx. If the update goes through, then the old web server is deleted. This is known as immutable infrastructure. Immutable means unchanged or something that you cannot change. As a consequence, with immutable infrastructure, we cannot carry out in-place updates of the resources anymore. This doesn't mean that updating web servers this way will not lead to failures. If the upgrade fails for any reason, the old web server will be left intact and the failed server will be removed. As a result, we do not leave much room for configuration drift to occur between our servers, ensuring that it is left in a simple, easy to understand state. And since we are working with infrastructure as a code, immutability makes it easier to version the infrastructure and to roll back and roll forward between versions. Terraform as an infrastructure provisioning tool uses this approach. Going back to our example, updating the resource block for our local file resource and changing the permission from 777 to 700 will result in the original file to be deleted and a new file to be created with the updated permission. By default, Terraform destroys the resource first before creating a new one in its place. But what if we want the resource to be created first before the old one is deleted, or to ignore deletion completely? How do we do that? These can be done by making use of lifecycle rules in our resource block, and we'll see how to do that next. In this section, we will learn how to set up lifecycle rules in Terraform. Previously, we saw that when Terraform updates a resource, it treats the infrastructure to be immutable and first deletes the resource before creating a new one with the updated configuration. For example, if we update the file permissions on our local file resource from 777 to 700 and then run Terraform apply, you would see that the older file is deleted first and then the new file is created. Now, this may not be a desirable approach in all cases. And sometimes you may want the updated version of the resource to be created first before the older one is deleted. Or you may not want the resource to be deleted at all, even if there was a change made in its local configuration. This can be achieved in Terraform by making use of lifecycle rules. These rules make use of the same block syntax that we have seen many times so far, and they go directly inside the resource block whose behavior we want to change. The syntax of a resource block with a lifecycle rule looks like this. Inside the lifecycle block, we add the rule which we want Terraform to adhere to while updating resources. And one such argument or a rule is the create-before-destroy rule. Here, we have the same resource block that has been updated with the lifecycle rule of create-before-destroy set to true. This rule ensures that when a change in configuration forces the resource to be recreated, a new resource is created first before deleting the old one. Now, there would be cases where we do not want a resource to be destroyed for any reason. For this, we can make use of the prevent destroy option. When it is set to true, Terraform will reject any changes that will result in the resource getting destroyed and display an error message like this. This is especially useful to prevent your resources from getting accidentally deleted. For example, a database resource such as MySQL or PostgreSQL may not be something that we want to delete once it's provisioned. One important thing to note here is that the resource can still be destroyed if we make use of the Terraform destroy command. This rule will only prevent resource deletion from changes that are made to the configuration and a subsequent apply. The last argument type that we are going to see here is the ignore changes rule. This lifecycle rule, when applied, will prevent a resource from being updated based on a list of attributes that we define within the lifecycle block. To understand this better, let's make use of a sample EC2 instance, which is a virtual machine on the AWS cloud. This EC2 instance is to be used as a web server and can be created with a simple resource block like this. Now don't worry if this resource block and the arguments look unfamiliar. We will cover it in much more detail in the EC2 section of the course. But for now, please note that the resource called web server makes use of three arguments. The AMI and the instance type are used to deploy a specific type of VM with a predefined specification. In this case, the values that we have chosen deploys a Ubuntu server with 1 CPU and 1 GB of RAM. We are also making use of a tag called name, which has a value of project A web server using the tags argument, which is of type map. When we run Terraform apply, the EC2 instance is created as expected with a tag called name and a value of project A web server. Now, if changes are made to any of these arguments, Terraform will attempt to fix it during the next apply as expected. For example, if we modify the tag called name and change its value from project A web server to, say, project B web server, either manually or using any other tool, Terraform will detect this change and it will attempt to change it back to what it was originally, which is project A web server. In some rare cases, we may actually want the change in the name via any other method to be acceptable, and we want to prevent Terraform from reverting back to the old tag. To do this, we can make use of the lifecycle block with ignore changes argument like this. The ignore changes argument accepts a list as indicated by the square brackets, and it will accept any valid resource attribute. In this particular case, we have asked Terraform to ignore changes which are made to the tags attribute of this specific EC2 instance. If a change is made to the tags, a subsequent Terraform apply should now show that there are no changes to apply. The change made to the tags of a server outside of Terraform is now completely ignored. And since it's a list, we can update more elements like this. You can also replace the list with the all keyword. And this is especially useful if you do not want the resource to be modified for changes in any resource attributes. We will learn more about lifecycle rules later in the course when we work with AWS resources. But for now, here is a quick summary of the 3 argument types that we have seen in this lecture. And now let's head over to the hands-on labs and practice working with lifecycle rules in Terraform. In this section, we will take a look at data sources in Terraform. We know by now that Terraform makes use of configuration files along with the state file to provision infrastructure resources. But as we saw earlier, Terraform is just one of the infrastructure as a code tool that can be used for provisioning. Infrastructure can be provisioned using other tools such as Puppet, CloudFormation, SaltStack, Ansible, etc. Not to mention ad hoc scripts and manually provision infrastructure, or even resources that are created by Terraform from another configuration directory. For instance, let us assume that a database instance was provisioned manually in the AWS cloud. Although Terraform does not manage this resource, it can read attributes such as the database name, host address, or the DB user and use it to provision an application resource that is managed by Terraform. Let's take a simpler example. We have a local file resource called pet created with the contents "we love pets." Once this resource is provisioned, the file is created in the /root directory, and the information about this file is also stored in the Terraform state file. Now let's create a new file using a simple shell script like this. Quite evidently, this file is outside the control and management of Terraform at this point in time. The local file resource that Terraform is in charge of is pets.txt under the root directory, and it has no relationship with the local file called dogs.txt, which is also created under the /root directory. The dogs.txt has a single line that says "dogs are awesome." We would like Terraform to use this file as a data source and use its data as contents of our existing file called pets.txt. If we want to make use of the attributes of this new file that is created by the bash script, we can make use of data sources. Data sources allow Terraform to read attributes from resources which are provisioned outside its control. For example, to read the attributes from the local file called dogs.txt, we can define a data block within the configuration file like this. As you may have noticed, the data block is quite similar to the resource block. Instead of the keyword called resource, we define a data source block with the keyword called data. This is followed by the type of resource which we are trying to read. In this example, it's a local file. This can be any valid resource type for any provider supported by Terraform. Next comes the logical resource name, into which the attributes for a resource will be read. Within the block, we have arguments, just like we have in a normal resource block. The data source block consists of specific arguments for a data source, and to know which argument is expected, we can look up the provided documentation in Terraform registry. For the local file data source, we just have one argument that should be used, which is the file name to be read. The data read from a data source is then available under the data object in Terraform. So, to use this data in the resource called pet, we could simply use data.localfile.dog.content. These details are of course available in the Terraform documentation under data sources. Within the documentation and under the attributes exported, we can see that the data source for a local file exports two attributes, the content and the base64 encoded version of the content. To distinguish between a resource and data sources, let's do a quick comparison. Resources are created with the resource block and data sources are created with the data block. Resources in Terraform are used to create, update and destroy infrastructure, whereas a data source is used to read information from a specific resource. Regular resources are also called managed resources, as it's an extension which is managed by Terraform. Data sources are also called data resources. That's it for this lecture. Now let's head over to the hands-on labs and practice working with data sources in Terraform. In this lecture, we will take a look at meta-arguments in Terraform. Until now, we have been able to create single resources, such as a local file and a random pet resource using Terraform. But what if we want to create multiple instances of the same resource? Say, 3 local files, for example. If we were using a shell script or some other programming language, we could create multiple files like this. In this example, we have created a bash script called createfiles.sh, which uses a for loop to create empty files inside the root directory. The files will be called pet followed by the range from 1 to 3. While we cannot use the same script as it is within the resource block, Terraform offers several alternatives to achieve the same goal. Now, these can be done by making use of specific meta-arguments in Terraform. Meta-arguments can be used within any resource block to change the behavior of resources. We have already seen 2 types of meta-arguments already in this course. The depends on for defining explicit dependency between resources, and the lifecycle rules, which define how the resources should be created, updated, and destroyed within Terraform. Now, let us look at some more meta-arguments, specifically related to loops in Terraform. In this lecture, we will take a look at the for each meta-argument and its uses in Terraform. In the previous lecture, we saw that when we use count, the resources are created as a list, and this can have undesirable results when updating them. One way to overcome this is to make use of the for each argument instead of count, like this. Next, to set the value of file name to each element in the list, we can make use of the expression each.value, like this. However, there's a catch. If we run Terraform plan now, we will see an error. The for each argument only works with a map or a set. In the variables.tf file, we are currently making use of a list containing string elements. There are a couple of ways to fix this. Either change the variable called filename to the type set. In the variables lecture, we learned that a set is similar to a list, but it cannot contain duplicate elements. Once we change the variable type and then run Terraform plan, we should see that there are 3 files to be created. Another way to fix this error, while retaining the variable type as a list, is to make use of another built-in function. This time, we'll make use of the toSet function, which will convert the variable from a list to a set. Once this is done, Terraform plan command should now work as expected. Now let us replicate the same scenario as the one we did earlier with the count meta argument, and delete the first element with the value /root pets.txt from the list. When we run Terraform plan now, we can see that only one resource is set to be destroyed, the file with the name pets.txt. The other resources will be untouched. To see how this is working, let us create an output variable called pets to print the resource details like we did with the example using count. From the Terraform output command, we can now see that the resources are stored as a map and not a list. When we use for each instead of count, the resources are created as a map and not a list. This means that the resources are no longer identified by the index, thereby bypassing the issues that we saw when we used count. They are now identified by the keys, which are file names /root/dot.txt and /root/cats.txt, which are used by the for each argument in the configuration file. If we compare this to the earlier output that we got when we used count, we can see the difference in how the resources are created. The count option created it as a list, and the for each created it as a map. There are a few other meta arguments in Terraform, such as provisioners, providers, backends, etc. We will see that later in this course. Now let's head over to the hands-on labs and practice working with the for each meta argument in Terraform. In this lecture, we will see how to make use of specific provider versions in Terraform. We saw earlier that providers use a plugin-based architecture and that most of the popular ones are available in the public Terraform registry. Without additional configuration, the Terraform init command downloads the latest version of the provider plugins that are needed by the configuration files. However, this is not something that we may desire every time. The functionality of a provider plugin may vary drastically from one version to another. Our Terraform configuration may not work as expected when using a version different than the one it was written in. Fortunately, we can make sure that a specific version of the provider is used by Terraform when we run the Terraform init command. The instructions to use a specific version of a provider is available in the provider documentation in the registry. For example, if we look up the local provider within the registry, the default version is 2.0.0, which is also the latest version as of this recording. To use a different version, click on the Version tab, and it should open a drop-down with all the older versions of the provider. Let us select version 1.4.0. To use this specific version of the local provider, click on the Use Provider tab on the right. This should open up the code block that we can copy and paste within our configuration. Here, we are making use of a new block called Terraform, which is used to configure settings related to Terraform itself. To make use of a specific version of the provider, we need to make use of another block called Required Providers inside the Terraform block. And inside the Required Providers block, we can have multiple arguments for every provider that we want to use. In this example, we have one argument with the key called local for the local provider. The value for this argument is an object with the source address of the provider and the exact version that we want to install, which in this case is 1.4.0. With the Terraform block configured to use the version 1.4.0 of the local provider, when we run a Terraform init, we should see a message like this. Before we wrap up this lecture, let us look at the syntax used to define version constraints in Terraform. In the configuration for the local provider, we have specified version equal to 1.4.0. This allows Terraform to find and download this exact version of the local provider. However, there are other ways to use the version constraint. If we use the not equal to symbol instead, Terraform will ensure that this specific version is not downloaded. In this case, we have specifically asked Terraform to not use the version 2.0.0, so it downloads the previous version available, which is 1.4.0. If we want Terraform to make use of a version lesser than a given version, we can do that by making use of comparison operators like this. And to make use of a version greater than a specific version, we can make use of the greater than operator like this. We can also combine the comparison operators like this to make use of a specific version within a range. In this example, we want to make use of any version greater than 1.2.0 but lesser than 2.0.0, but also not the version 1.4.0 specifically. As a result, Terraform downloads the version 1.3.0, which is acceptable in this case. And finally, we can also make use of pessimistic constraint operators. This is defined by making use of the tilde greater than symbol like this. This operator allows Terraform to download the specific version or any available incremental version based on the value we provided. For example, here we have given the value of 1.2 following the tilde greater than symbol. This means that Terraform can either download the version 1.2 or incremental versions such as 1.3, 1.4, 1.5, all the way up until 1.9. However, if we look at the provider documentation, we do not have a version 1.5 or anything above. The maximum version that we can make use of in this case is 1.4.0, and this is the version that is downloaded when we run Terraform init. Let us make use of another value, this time 1.2.0 with the same pessimistic constraint operator. This time, Terraform can download the version 1.2.0 or the version 1.2.1, or the version 1.2.2, all the way up until 1.2.9. Again, we only have a maximum version of 1.2.2 in the registry, and that's the version that will be downloaded when we run Terraform init. Well, that's all for now. At KodeKloud, we have multiple learning paths curated just for you to help you to go from a beginner to an expert in various DevOps technologies. So don't forget to check it out. And don't forget to subscribe to this channel as we publish more courses very often.